We'll continue now the implementation by creating an implementation of this interface for an undirected graph unlabeled using adjacency lists. And let me make this bigger so you will be able to see the code. Now, as in previous file, I no longer put the comments. So when you create your implementation, you need to add your comments based on your understanding and my explanation in this video. Comments are very important, so be sure you add them. Now, these are the imported files. You can import them as you don't need to write them now. You can import them as you need them when you write the code. So as a data structure, we'll use a adjacency list for each element in for each vertex. We'll keep the list of adjacent vertices. So this is how we store the graph. And for more explanations, please refer to the textbook. Now, we have a few constants. Now, because we are able to add and remove things, and we use dynamic capacity arrays to save the elements in the graph, we need to be able to double and half the arrays. And one issue when you half is when you will half an array. And we use here as a trigger when we got 1/5 used of an array, then we'll have the array to make space for other elements. So that will be the trigger when we have 1/5 of the array occupied. Now, sure, we'll double it when we reach the size. It makes no sense to double before because you don't know if you need more than the current size. And also we specify an initial number of neighbors, like 10, like the capacity for 10 neighbors. When we create an adjacency list, that's how much we'll reserve. Now, because some elements will not have neighbors and we want to be able to easily specify that, we define like a constant, an empty array that will have no, that will specify that there are no neighbors for a given vertex, and we'll use this as an initialization. So let's start by looking at the data structure. We'll keep the number of vertices, the minimum capacity is capacity under which we don't want to go. It's okay, this is the initial or minimum capacity, we'll keep it always. Also, we'll keep the number of edges that are currently defined. And for each vertex, we'll keep the degree explicitly, just to know how many neighbors I have for each vertex. Sure, you can compute that, but it's much easier to keep, and we need it in order to see how much of an adjacency list is occupied and how much is still available. Now, the adjacency list will keep for each vertex an array of integers with the indexes of its neighbors. So this is what the adjacency list is. We need a constructor, and the constructor will specify a number of vertices and will construct a graph only with these vertices, no edges, for the given number of vertices. So sure, the number of vertices of the graph is the one provided. There will be no edges, and we put the minimum capacity being this number of vertices. So we'll not reduce the number, the capacity of the arrays under this capacity, make no reason to do it. Then we will initialize the arrays for degrees and adjacency lists, and based on this number of vertices. So for each vertex, we'll put the degree 0 and the corresponding adjacency list being an empty array. So this creates a graph only with the vertices, n vertices, number of vertices. Now, let's start to see how we process the vertices. And to get the number of vertices, we just return the number that it's stored. To add a new vertex means we want to increment the number of vertices. So first of all, we need to see if we have available space. If we don't, if my number of vertices is the current length for the arrays, and here we know that the vertices degrees and the adjacency list have the same length. So if I have reached this length, means I need to double the capacity. So I double the capacity, so I make space for more vertices. Now, we'll discuss a little bit later how we double the capacity, but this is similar how we double the capacity for all dynamic capacity arrays. It's just that we put the code in clear in our graph code. Now, after we make space for a new vertex, we specify that the adjacency list for this vertex will be the empty array, and sure it will have the degree of 0 because it has no neighbors, and we increase the number of vertices. So this is how we add a vertex. If we want to remove one, very similar. First of all, we need to look that it's a good index that is provided. To be a good index needs to be between 0 and the maximum number of vertices, excluding that one. If not, it's a wrong index. Then we need to remove all the edges associated with this vertex, because deleting the vertex, all the edges adjacent with it will disappear. So we remove the edges between this vertex index and the current index, the current adjacent vertices for this vertex. So we get rid of those. Now we have like an isolated vertex, so we can take it out. And again, the idea to remove will be that this index will disappear, and I take the last element, the last vertex, and renumber that last vertex for this index. So my degree for the index now becomes a degree of the last vertex, and the adjacency list of this index will become the adjacency list of the last vertex. So effectively, I move the last vertex in the position of the deleted index. I renumber it. And sure, now I have fewer vertices. So that's why it's a little bit difficult with the remove, because it's also a process of renumbering of the vertices that is involved. Now, after we reduce the number of vertices, we need to see if we need to halve the capacity. And we have the capacity when the length of the vertices is more than twice the minimum capacity. And so make no sense to half it if I will go under the minimum capacity after half. And also we have a trigger for the length compared with how many vertices I have. So here we use a half capacity trigger to be sure that I have quite a few, under 1/5 of vertices from the current capacity. So then makes sense to have the capacity for the arrays. So after that, what we want to do is to renumber all allows you in the adjacency list to renumber the two vertices, the ones deleted. We will now become, will replace the the previous last vertex. So which has a number of, which has a previous number was number of vertices, and current number needs to be vertex index. So I go through the adjacency list, and every time when I find a number of vertices, I will replace that with the new number vertex index. So you see, when I remove, I take out the previous vertex and I renumber the last vertex with the index of the taken out element. It's the easiest way to remove. So some other remove strategy will be to switch all the vertices, but in that case you will need to renumber a lot of edges. So this way you just renumber the edges for the last vertex. Now, for the dynamic vertex capacity, as I said, it's very similar with the dynamic arrays. So basically, you have a double or a half vertex capacity, and both of them will call the same change vertex capacity, providing a new capacity. And this assumes these are private methods, and they assume that they are called when this operation makes sense and doesn't lose data. So there is no test here, because when you call them from this class, that's why they are private. You need to take to be sure that you do your checks to not to lose data. So if we specify the new capacity, what we do, we create new arrays and copy the previous values in the new arrays. So we have basically two arrays that needs to be that need to change the capacity will be the vertices degrees and adjacency list. So for the vertices degrees, we create a new array with a new capacity, and we copy all the degrees from the previous from the current vertices degree in this new one, and then the current one becomes this new one, which will have the new capacity. And same for the adjacency list, copying all the current adjacency list, and then the new adjacency list become the current adjacency list. So it's the classical code to change the capacity of the stored arrays. Now, let's look how we work with the edges. We keep the number of edges because it's much easier to keep it than to compute each time when you need it. Sure, it starts with 0, and then as you add edges, it will increase. As you remove edges, it will decrease. And for given vertex, you can get the number of adjacent edges, which is also named the degree of the vertex. So you can, this is also stored in clear in the array vertices degrees. Now, to get all of these neighbors, all of these adjacent vertices, you have two ways. You can call an iterator over integers that will return each neighbor one by one as they are stored in your adjacency list. And this is just an iterator over an array. It's again very easy implementation. Or you can create a copy of the adjacency list, and it turns the entire array of integers as a copy of the data, which is done in this method. So both of them will allow you to process the neighbors of a given index. Now, to add an edge, first you need to check that the two vertex are correct, and then you will add a directed edge. Why? Because if we want to to add an edge between vertex 3 and 5, you will need to put 5 in the neighbors of 3, but also 3 in the neighbors of 5. So in the adjacency list for 5. So add the directed edge, which is private, is doing like that. It's putting vertex 2 in the adjacency list for vertex 1. And as you can see, we call this to add vertex 2 in the adjacency list of vertex 1, but then we call to add vertex 1 in the adjacency list of vertex 2. So we make double links in the adjacency list. And this is how an undirected graph is always stored, because it doesn't matter from when you add an edge, you can go from 3 to 5, but also from 5 to 3. So you keep both directions. That's why it's named undirected graph. So uh, to add a link for in one direction, what you do is first you see that you have space in your adjacency um, list, and if you don't, if your adjacency list is full, you just double the capacity for the adjacency list, and if not, you will put the index of the second vertex at the end of your adjacency list, and you will increase the degree of the adjacency list. You see, it's two operations here. This returns the current degree and increases with 1 the degree, and then in this last position in your adjacency list is added vertex to index. So this will guarantees that both adjacency list and vertices degrees are updated. Now, the number of edges is updated only once, because when you add an edge between vertex 1 and vertex 2, you add a single edge. Even if you store it in two places, it's considered a single edge. That's why it's added here in the main. Now to remove, it's very similar in the sense that I check first the indexes that these are correct indexes to remove. Then you remove the directed edge of vertex 2 from vertex 1, and you remove the directed edge from in vertex 2, the neighbor vertex 1. So you do, again, the two directed edges that we added, now we remove them. And to remove one of them, you just go in your adjacency list for vertex 1 index, and when you find vertex 2 index, you need to remove that. How we remove? We take the last one and put instead of, we take the last neighbor and put it instead of the remove neighbor. So like we did with the vertices. And sure, the number of the degree of the vertex 1 will decrease, and also we need to check if we need to have the adjacency capacity after the remove, which is similar with how we have the capacity for vertices. Now, for the dynamic edge capacity, so for each adjacency list, it's a dynamic capacity array. So we do the same. So we have a change adjacency capacity, and then we check to see when we want to add to double. Now, the only observation is that we start with empty array, so we need to be sure that if it's an empty array, we'll start with the initial adjacency capacity, but if it's not an empty array, then we'll double the current capacity. So that's just to take in account that we start with empty array have a capacity of 0, so if you double it will remain 0, it will not help. So that's why we need this a little bit more complex code here to allow empty arrays as the initial adjacency list for a vertex. Now, the change, it's similar with the previous change in the sense that we just create a new adjacency list, put all the neighbors in this new adjacency list, and then update the adjacency list of our vertex to be this new adjacency list that has the right capacity. The last two things that we'll discuss is how to read, how to get a graph from a file, and how to output a graph in a string. So to get a graph from a file, we receive the file, we create a scanner for this file, and then we read, by convention, we'll read first, and here are the examples. These are exactly the syntax used in the textbook. First number of vertices, number of edges, and then each edge like a pair of vertex 1, vertex 2, with no rule in which order they appear. So we read the number of vertices, the number of edges. We create an undirected graph for this number of vertices, and then we read all the number of edges one by one, and we create, we add the edge to our graph. So based on linking the vertex 1 with vertex 2 that are read from the file. So for instance, we read 0, 5, we add the edge from 0 to 5. And at the end, we return the graph. Now to output, we'll output the graph as a pair of vertices and edges. Now for the vertices, because they are actually here needs to be 0. First vertex is 0. So we'll start with 0, and we'll go to the number of vertices minus 1. This is how we go. Okay, so we'll go from 0 to number of vertices minus 1, and then we'll specify the edges as a set of pairs where each we will have index of the vertex and of its adjacent node. Now, keep in mind these are duplicated. In order not to duplicate them, we'll just put the conditions that will not print all the neighbors, but only the neighbors that are greater than a given vertex. In this way, we'll avoid to put 0, 3, and 3, 0 twice as edge. We'll put only 0, 3 because only that one 0 is less or equal with 3. Now, let's see now how this will work in the next video. We'll have a short test for our method.